Hi, in this video, we're going to take a look at orthogonal arrays for experimental design. Okay, so why do we care? Well, if I'm doing experimental design, I'm trying to set up my experiment before I collect my data, before I do my analysis, to make sure that the data that I ultimately get is as informative as possible. Okay, well, one thing that we would like to have with perfect data would be independence between our columns of data. Well, orthogonal arrays give us a way to guarantee that the data that we're going to be getting will have independent, orthogonal, perpendicular columns between our independent variables. Okay, so the idea is I am going to do an experiment. I'm going to do a bunch of runs, and so I'm going to pick the independent variable values that give me the most informative data that I could possibly get in relation to my dependent variable. All right, so orthogonal arrays. Now, what is the difference between a data frame, a matrix, and an array? All right, so a matrix technically is a rectangular table of mathematical elements, and those mathematical elements have to be from a field. Typically, these will be just regular old numbers. Now, when we talk about an array could technically be anything. I could have anything in any position. I could have, an array of arrays. I could have an array of matrices, an array of smiley faces. And from a math point of view, by the math definition, an array is anything. A data frame has to be for data, and we classify the types of data that we have for that. Okay, so uh, orthogonal arrays are a class of statistical designs used extensively in experimental designs and combinatorial mathematics. They're also used in numerical linear algebra. Linear algebra, they are used up, down, left, and right. Most of my time with them is actually with Fourier analysis. They're super important in all of math. They're structured arrays of numbers or symbols that satisfy specific mathematical properties, making them highly useful for designing experiments, where the goal is to study the effects of multiple factors simultaneously in an efficient and balanced way. All right, so what are their features? All right, so they're going to give balanced representation of the factor levels. So when I say balance, that means that we don't have a clumping. We don't have an over proportion of one particular level of a factor. We want to have it like evened out for every factor. In an orthogonal array, each combination of factor appears an equal number of times, ensuring balance. This property helps minimize bias and allows for an unbiased estimate of effects. Orthogonality, so also perpendicular zero correlation, is a byproduct of this. The columns of an orthogonal array are orthogonal, meaning that any pair of columns is statistically independent from each other. This property allows for isolation of individual effects of factors during an analysis. Okay, so uh, let's go ahead and like make a mathematical notation for this. Let's say that OA of NKST is an orthogonal array with capital N rows, K columns or factors. Notice it does not have to be a square matrix or a square array, I mean. S is the number of levels for each factor. Typically, we're going to have the same, but this could be a vector or it could be a list, depending if you're working in Python. And T is the strength of the array. This represents the maximum level of interactions that can be studied. It specifies that all combinations of level for any subset of T factors appears equally often. And we have a regular structure. Orthogonal arrays often follow structured rules that make them deterministic, reproducible, and easily interpretable. And so in my experimental design, if I have the luxury of using an orthogonal array, I'm basically stacking the deck to make sure that my data is as informative as possible. All right, now applications of orthogonal arrays, I mean, it's up, down, left, right, everywhere. If math is happening, highly likely that orthogonal array is happening. And when I say orthogonal array, that will include orthogonal matrices, orthogonal data frames. So used everywhere. So widely used in experimental designs, such as Taguchi methods for quality engineering, and also full factorial designs, partial factorial designs. These designs allow researchers to study multiple factors with fewer runs than a full factorial design, while still capturing critical information. All right, so let's talk about a few examples of orthogonal arrays. We've got full factorial designs. And so this is a special case where we get maximum possible strength off of our data. Now, full factorial designs require a lot of runs to be able to get that full effect of the data, and that typically isn't possible. So we're going to have to make some choices, and we could do a fractional factorial design or a Taguchi design. Fractional factorial designs are designed from orthogonal arrays by selecting a subset of runs that preserves orthogonality for special interactions, and Taguchi designs. These are orthogonal arrays tailored for robust design and quality engineering, especially for situations where factors and levels are unbalanced. So let's look at a simple example. Let's look at orthogonal array with n runs, 4 factors, 3 levels each, and we want to have we want to be able to pick up two-way interactions off of this. Okay, so here's just an example, and here I've got the simplest possible numbers representing this: levels 1, 2, and 3. Now, you'll notice that the arrays are always balanced off of this, that I've got 3 1s, 3 2s, and 3 3s every single time. We're now some orthogonal arrays in Python. The simplest way to generate an orthogonal array in Python is to use itertools product and take the list of what I've got. And so if I've got discrete levels set up, that I just iterate through all of them. And so we can see this. Now, how do I know that this is orthogonal? Well, think about it for a moment. I've gone through every possible combination of column 0 and column 1. Because I've gone through every single possible combination, the distributions have to be independent. All right. So they're independent, therefore they're have zero correlation, and we're going to have orthogonal off of that. And just to prove it to you, if I compute the correlation, you can see that I have a perfect, zero correlation, between the columns, and of course a correlation of one of a column with itself. Now, here is something that I'm going to say. Orthogonal arrays are a lie. Now, that's not 100% true, but nowadays you got to say something extreme to be able to get people to pay attention. Orthogonal arrays are a lie. Orthogonal arrays refer to arrays that would be orthogonal if the columns were centered by subtracting the means. These non-centered arrays have zero correlation between distinct columns. Okay, so when we talk about orthogonal arrays, we actually mean zero correlation is what we actually want. We don't actually care if it's a zero dot product or not. Orthogonal perpendicular doesn't really matter. So let's take a look at this. Okay, so how do we compute orthogonality? Well, what I do, I take the pairs of values, multiply them, add them all up. If it's orthogonal, then I end up getting 0. All right, well, if I look through here, if I look through the pairs of A and B, and you can take any 2 pairs off of this, you'll notice that every single time the multiplication is positive. Since the multiplication is positive every single time, when I add it up, I have to get a positive number. Therefore, it is impossible for this orthogonal array to be orthogonal. Okay, so that's why orthogonal arrays are a lie. Now, when it comes to actual experimental design, it's okay, it's fine, because if I subtract the mean, if I subtract 2 from every single column, then I will get orthogonality. And no matter what, I'm going to have zero correlation between each column. So let's go ahead and verify that. Okay, so here I went through and took the same code as before. If I go and I compute the dot product between the transpose of the array and itself, then you can see that this is not orthogonal. Orthogonal means the 36 would be a 0. So no, no, absolutely not. This is not orthogonal. But if I compute the correlation, I see, hey, I've got 0 correlation. All right, well, if I go through and subtract the mean from each column, you'll notice that, boom, now I do have orthogonality. Now, you also notice that these are not orthonormal, but that's okay. That really doesn't matter for our purpose. If I want normality, what I'm going to do when I have my independent variables that are numeric, I'm going to select values that will give me standard deviation 1. All right, so let's look at some example arrays that are available to us in Python. All right, so if I use the orthogonal array package, there are example arrays. Now, when I look at this, it doesn't give me the full information about it. It doesn't print it. If I want to actually see the array, I need to invoke NumPy array to make it into an array. And I always prefer data frames. So I'm going to go ahead and pass this to pandas. And if I want to go a step further and set it up so that I have -1 and 1s off of this and zeros, I can multiply by 2 and subtract 1. Not in that order, though. Subtract 1, then multiply by 2. All right, so let's just take a look at what these look like for us. So here I'm going to use list comprehension to kind of show what's up. All right, and so notice I've got the verbose. The verbose says, hey, print information about this when I do this. If the verbose is 1 or greater, I'm going to get the same information. I put down 10 because I was trying to see, will I get more if I put in 10 or 20 or something? Now I got the same as 1. Now these are example arrays. These aren't in a true like order. Several of these are useful in Taguchi designs. Most of these are not. But we can go through. So the first number is the number of runs. So this first one has 8 rows. That's the number of runs. We have 2 factors, and we can see that we've got 2 levels for each factor. Just setting that up. Okay. And we can just scroll down and see what we've got throughout. And if I look at the shape so here I'm calling shape on the data frame after it's pandas. And you can see here, I can see the number of runs and the number of factors, the number of independent variables. All right, when to use orthogonal arrays? When I'm testing multiple factors efficiently, situations where conducting a full factorial experiment is too costly or time consuming. I'm trying to do an optimization process. Taguchi was big on that. In manufacturing, agriculture, or other domains needing quality optimization and structured data sampling. So I want to reduce redundancy and improve sampling coverage in simulation studies. All right, so now Taguchi orthogonal arrays. Here, these are the ones that appear in a Python package that we'll talk about later. And I looked up online and found all of these Taguchi arrays that these are named arrays that we can invoke. All right, so that's what I've got. Hope you enjoyed this. Life is short. Do math.